Let's see convolution theorem in Z transform. We are studying Z transform. So what is convolution theorem? Although we haven't studied inverse Z transform yet, but this is more of a Z transform than inverse Z transform. So let's study it first. Convolution theorem. Let's say we have two functions un and vn. The Z transform of un is uz and Z transform of Vn is Vz. Okay, that is to say that Z inverse of uz is un. Clear? And from here Z inverse of Vz is Vn. Okay. In this condition, if we have to take Z inverse of uz into Vz, that is, if we have a function which can be considered to be product of two functions of Z, then in taking inverse of them is nothing but it is transform, which you can write like m equal to 0 to n u. So it will be u m and then second one v n minus m. This is your transform, and it is written like this: u1 convolution vn. This sign is convolution. Clear? So convolution convolution theorem. So for Z transform, the convolution theorem is like this: if u uz and vz correspond to un and vn, then Z inverse of uz and vz is m equal to 0 to n summation um vn minus m. It is written as un asterisk star vn, which is said un convolution vn. Okay, we'll see an example and understand this. Let's say we have a function of z which is z square by z minus a into z minus b. We have to take inverse of this, that is z inverse of f z. What we can do, we can write it like this: z by z minus a into z by z minus b. Okay, you know what is the inverse of this? This is very standard. What it is? It is 1 by a by z here and into 1 by 1 minus b by z. You know this is the inverse of, if you take z inverse of this function, that is z inverse of this function. So inverse of this is a to the power n here, and inverse of this is b to the power n. You know this is this. Clear? Why? Z transform of a to the power n into 1 will be u of z by a. This you know. And for 1 it is z by z minus 1. So it will be z by a by z minus 1. So z by a minus 1. It is this. So if you take, it comes to z by z minus a. See this one. Therefore inverse of this is a to the power n. Clear? So this is basically a to the power n convolution b to the power n. So now let me rub this. Clear? Now we will take the transform. So z inverse of this function is basically a to the power n. This is the first sequence, convolution second sequence, and you have seen that this is given as m equal to 0 to n, first function, so a to the power m, and second function b to the power n minus m. This is from convolution theorem. So what you can write, we can take b to the power n out because m is the variable here. See, m varies from 0 to n. So m will be here inside the summation and n we can take out. So this will be b by n, m equal to 0 to n. See, this is a to the power m, b to the power minus m. So it will be a by b to the power m. So if you expand it, you get b to the power n. Putting 0 will be 1, then a by b, then a by b square up to where? N to the power n, that is a to the power, a by b to the power n. This is a geometric progression with ratio a by b. You know what it is? It is a by b, the ratio, to the power n plus 1 minus 1 by a by b minus 1. So what you get? See, this is a to the power n plus 1 by b to the power n plus 1. If you multiply, you will get b in the denominator. Okay, so what you will get is, you will multiply both. So b in the denominator here. Now if you, let me do this. This is basically a n plus 1 by b to the power n into b to the power n plus 1. So it is b. Minus here you'll have b. This goes here, and then plus n. This by a by b minus 1. So now what you get? If you take this, so b will be cancelled. Finally, what you will get? The answer that you will get is, I am writing it here. It will be a to the power n plus 1 minus b to the power n plus 1. B cancel. Here you have a minus b. Okay, so this is the answer. Okay, so you see, you can use convolution theorem to find the inverse when you know the individual sequence for two different functions. Okay. Now let's see a very important concept that is called region of convergence. What it is? Now, see, we have up till now we have seen sequences in the transform for which n is greater than equal to 0. We have seen this only these sequences. We have found the Z transform of these sequences only, that is where n is greater than equal to 0. So if you plot n on number line, so we have up till now been doing this only, this side only. This is the right sided, called the right sided values of n. So we have seen values of un on the right sided n plot only, but we can have for n less than 0 also, that is left side also. Okay, so for that we'll have to understand what is the region of convergence. See, I told you we have seen Z transform of un as n equal to 0 to infinity, un z to the power minus n. This is only right sided description of the sequence. We can have this from minus infinity to infinity, that is left sided also, this side also. Clear? And what is region of convergence? A region of convergence, in short we write ROC. This is the n-axis. If we talk of Z plane, the region in which this sequence converges absolutely is called region of convergence. Okay, the definition is the region on the Z plane where this uz converges absolutely, that is your un converges absolutely, the transform of un converges absolutely, is called a region of convergence. And for n greater than equal to 0, in the starting only we had seen this is possible for this when z is greater than a. We had defined this in the start only for particular values. That is, if you see as in a circle, if this is the radius, a is the radius, we have region of convergence out of this, that is z is out of this, greater than this. On the contrary, if you see the left hand side, that is region of convergence for n less than 0, z is greater than a. Similarly, you will find there that is z is less than b, another circle. That is, if this is b, then this is the region. The sequence will converge inside this circle only. Okay, so what happens when you have a sequence from minus infinity to infinity, from here to here, you have this side, the sequence converges for z greater than a, this side right sided, and this side left sided, this sequence converges for z less than b. A and b are some arbitrary value. So when you talk of here to here, what we are left with is an annular region. That is, let's say our b is greater than a, the value of b is greater than a, then this region, this radius is a, this radius is b. Then we have seen this is a out of a, so out of a but less than b. So this region is the region of convergence when we have sequence from minus infinity to infinity. Clear? When we have a sequence from 0 to infinity, this will be, there will be an arbitrary value a, out of which the z plane, out of which in the z plane the sequence converges. If we are talking of left side, that is n less than 0, then we will have a value b, inside that circle the sequence will converge. But when we talk of minus infinity to plus infinity, you will get an annular region, this, where it will converge. So let's see some examples and understand this. So let's see first example, simple example. The function is 2 to the power n for n less than 0. Up till now we had seen only for n greater than equal to 0. Now let's see for n less than 0. What will be z of fn? Z transform of fn by definition you know will be n equal to 0 to, this is less than 0. So n equal to minus infinity to 0? No. In a discrete system, we use n less than 0 and n greater than equal to 0. In discrete, n less than 0 starts from 1, minus 1. So it will come to minus infinity to minus 1, because the next is 0, which will be for the right side. So n minus infinity to minus n minus 1 to the power n z minus n. This we have to find this summation. What we do, let n be equal to minus m. Therefore, the limits will be, for m it is minus infinity, so it will be infinity, so let's write it here, and minus 1 will be 1. So 1 to infinity, so it doesn't make much difference. 0 to infinity or 1 to infinity is almost same, because this is infinity. And here we'll get 2 to the power minus m, see, and z to the power m. That is m equal to 1 to infinity z by 2 to the power m. So if you expand it, you'll get, when you put 1, so it will be z by 2, then 2, z by 2 square, z by 2 cube, and so on. What is it? You'll get, if you take z by 2 out, you'll get 1 plus z by 2 plus z by 2 square, and so on up to infinity. Now you know this is a geometric progression to infinity. When your z by 2, that is the ratio, is less than 1, this is actually, this z by 2 we take out, this is what? It will be 1 by 1 minus r, that is z by 2. This you know. So 2 you take upside, this cancels, the answer is z by 2 minus z. So this is the transform. And what is the region of convergence? Z less than convergence. That is, as we had discussed, if you draw a circle with radius 1, this inside this, the sequences converge. The sequence converges. Okay, clear? Now let's see one for n greater than equal to 0, and then finally we'll see a sequence which will be from minus infinity to infinity. Let's see. Our second example is 5 to the power n by factorial n for n greater than equal to 0. This is our sequence. So z transform of this function will be n equal to 0 to infinity. This will be 5 to the power n by factorial n z to the power minus n. So what we can write as, when you put 0, this will be 1, 1, 1. So the first value will be 1. When you put 1, it will be 5. Let's say this is to the power, so 5 by z to the power n. So we'll write 5 by z 1, and this is 1 factorial 1. Then 1 by factorial 2, 5 by z square, and so on. If you remember, this is an infinite series which is given as e to the power theta. This is for theta 1 plus theta by factorial 1 plus theta by factorial 2, sorry, theta square by factorial 2 plus theta cube by factorial 3, that is e to the power theta, and theta here is 5 by z. What will be the region of convergence? See, you can have z from minus infinity to infinity. You don't have any limit. For every value of L of z, this will be, the series will converge. That is, the value exists for all values of z. For all values of z, the sequence converges. Okay. So this is our example for n greater than equal to 0. Now let's see one example when we have a function from minus infinity to plus infinity. Let's see how to do that. So our third example is, let's say our fn is 4 to the power n for n less than 0, and it is 2 to the power n for n greater than equal to 0. Okay, this is our function. So z transform of this function, it will be first from n equal to minus infinity to minus 1, this function, and then the second function, that is n equal to 0 to infinity 2 to the power n z minus n. Now this, it is very simple, z by z minus 2. This is very simple, and the limit is what? Z by 2 less than 1. This is what? 2 by z less than 1, sorry, 2 by z less than 1. So what you get is 2 less than z, that is z greater than 2. From here the region of convergence is z greater than 2, and let's see for this one. We have done in the last example. Let's see. It will be, if we take m equal to minus n, we will have m equal to 1 to infinity, and this will be 4 to the power minus m. So what we will have is z by 4 to the power m, and this is this part. So here what you can do, when you put 1, it will be z by 4, then z by 4 square, and so on, and plus this one. So what we get is, see, if you take z by 4 outside of this, you get 1 plus z by 4 plus z by 4 square, and so on, and then you have this value, z by z minus 2. This is geometric progression, and if the ratio is less than 1, that is, your z by 4 is less than 1, then this can be written as 1 by 1 minus z by 4, and this you have z by z minus 2. This you understand? So from here what you get, z is less than 1, see, sorry, less than 4. You have z greater than 2, and this is z less than 4. Therefore the region of convergence here will be 2 z 4. That is, if you draw a circle, the outer will be 4, radius will be 4, the inner will be radius 2. This is the region of convergence, this annular region. This is clear? Now let's see this value. 4, it will go up, cancel. So you have z by 4 minus z plus z by z minus 2. So you can converge it also. So this is the result, and this is the region of convergence. I think this is clear to you. Solve some examples from book and you'll understand.